Okay, there is a new reading assignment, and the reading assignment is in the main textbook. Not read, but study chapter 3. Chapter 3 is essentially what we're talking about today in lecture. And so in terms of lecture topics, essentially the entire lecture is in one form or another about resting membrane potential. Except a little bit of catch up on stuff that I didn't cover last time. And a subtopic of that is that for resting membrane potential, there is a critical role for one particular ion, and that ion is potassium. And then I'm going to talk about equilibrium potential. Equilibrium potential is important for resting membrane potential, but it's also critical, it's a broad topic. It's also important for action potential, synaptic potentials. By the time we get to the midterm, you'll be really sick of the equilibrium potentials, I'm guessing. Okay? There's no chance in the world that we're going to get to the Nernst equation today. If I got there, it would mean I went way too fast, and I'd probably just stop at that point anyway. So, see if I can make this work without screwing up. No. I know. So, where we left off last time, I had talked about neurons, giving you the parts of the neurons, and the point that I started to make is that neurons have different functional zones. There is a zone of input, which is the dendrites and the soma, and that's the parts of the neuron that receive synaptic input. There's the zone of integration, that's the axon hillock. And that's where the synaptic potentials traveling from the point of origin at the postsynaptic membrane, traveling along the membrane or the axon hillock. At the axon hillock, those synaptic potentials are integrated, and a decision is made at the axon hillock whether or not the neuron should generate an action potential. If so, that action potential is then conducted along the zone of conduction of the axon toward the presynaptic terminal where the zone of output transmitter is released. Okay? And the point here is that even though all of those parts of the neuron have a cellular membrane, embedded within the cellular membrane of those different zones, there are different mechanisms, different molecules. So go down here to the molecular structure. In the zone of input, in the soma and the dendrites, you have one kind of ion channel, and that is the ligand-gated ion channel. The ligand is the general term for chemical that binds. In most of the course, we're talking about transmitter, that's the chemical transmitter that will bind those ion channels. So the soma and the dendrites have receptors, have ligand-gated, transmitter-gated ion channels. In contrast, the other parts of the neural membrane, the axon hillock, the axon, the presynaptic terminal, have different kinds of ion channels. So you travel along here to the zone of integration. that is the axon hillock, or the axon itself, the zone of conduction, or the terminal gluton, the zone of output. Here you see that you have voltage-gated ion channels, in contrast to the soma and dendrites, where you have receptors, ligand-gated ion channels. Okay? However, you have different kinds of voltage-gated channels in the zone in the zone for a minute, the axon hillock, and the axon as compared to the gluton. In the axon hillock and the axon, you have two types of voltage-gated channels. One of those types of voltage-gated channels is permeable to sodium. The other type of voltage-gated channel is permeable to potassium. That's true in the axon hillock. That's true in the axon itself. Basically, those channels are identical. They gate the same kind of ions. In contrast, the voltage-gated channels in the terminal gluton, you also have channels that gate sodium and potassium, but here you have a third kind of voltage-gated channel. In that case, it's a voltage-gated channel that gates calcium. Do I expect you to know all of that and understand all of that right now? No, I don't. I do want you to get that there are different kinds of mechanisms embedded in different parts of the neural membrane. All will be explained, right? But it's because of those different kinds of channels that in the soma and dendrites you have postsynaptic potentials, which are different from the action potentials that you have in the axon hillock and the axon, as well as in the terminal gluton. Right? So one of the chronic problems students have is distinguishing synaptic potentials from action potentials. Synaptic potentials and action potentials are different. They're the same in the sense that their voltage changes. They're different in terms of their function, and they're different in terms of their underlying mechanisms. Transmitter-gated channels for the synaptic potentials, voltage-gated channels for the action potentials. But so this is something that I don't expect you to get right now. Refer back to it, like before the midterm, and it'll make sense then, and it doesn't now. Okay. On to the main topic. The main topic being resting membrane potential, with lots of other things thrown in. Now, one of the challenges here, both for me lecturing and for you as students, is that you're given pieces of the puzzle little bit by little bit without having the whole picture. And so basically you need to bear with me, just trust me, all will be explained. If something isn't clear that I'm talking about, go ahead and ask questions. I may just say, well, I'm going to have to defer that because it's going to be explained. Okay, but don't hesitate to ask if it's not making sense. Okay, so what I'm talking about here in general are membrane potentials, more specifically the resting membrane potential. Okay, so what is the resting membrane potential? Okay, so resting membrane potential, the name itself is very descriptive. Resting membrane potential. The last word, potential, is another word for voltage. So it tells you that it's a voltage. Resting membrane tells you where the voltage is. It's a voltage across the membrane. And the resting means that it is the voltage across the membrane of a neuron in the absence of output. In the absence of input. So it's when the neuron is resting, you have a resting membrane potential voltage across the membrane. So when we start talking about that, here's the technical situation you have. Okay, neuron, obviously, with an electrode penetrating the cell membrane so that a voltmeter, typically an oscilloscope, is recording the difference in the membrane potential, the voltage from inside of the neuron to outside of the neuron. And that rest, the resting membrane potential, is typically given at negative 65 millivolts. 65 1,000th of a volt. Negative 65 1,000th of a volt. So we're not talking about a shocking value here. These are tiny values. Okay? And why is it negative? Well, if you take and look at this little insert down here, insert down here is supposed to represent the neuronal membrane, the lipid bilayer. The reason that the value in the voltmeter is negative is because there are more negatively charged ions inside intracellularly than outside. Okay? And the membrane voltage is negative. Now there's something deceptive about that particular little diagram because all it shows is negative charges inside and positive charges outside, anions inside, cations outside. But the reality is that's just a differential that creates negative voltage. The reality is that there are vast numbers of cations and anions intracellularly and vast numbers of cations and anions extracellularly. Okay? And so the percentage of the ions that create the voltage change is a trivial percentage of all of the ions that are separated. More on that later. Okay. Quick question, quick clarification question. Yeah. Louder. Yes, there are anions and cations inside of the neuron. There are cations and anions extracellularly as well. And so what's shown in the diagram is that there's a net greater number of anions intracellularly than extracellularly. Take all of them in combination. Is that the question? Clarification question. Okay, so let's now go and take this diagram and transpose it over to here. Okay, so this represents a neuron, symbolic representation of the neuron at rest. So you see that the intracellular voltage is minus 65 millivolts, and this represents a microelectrode that's penetrating the membrane. So that the reading on the oscilloscope is the voltage difference from inside to outside of the neuron. That's represented on the graph below. Here you have membrane voltage as a function of time. No particular units of time, but these are quick changes, so milliseconds, thousandths of a second. And only two units are given here. One is 0 millivolts, and the other is minus 65 millivolts, which is the resting membrane potential. Now, you understand that different neurons have different resting membrane potentials. In fact, when we talk about the visual system, you're going to learn that the photoreceptors have resting membrane potentials that are closer to minus 30 millivolts, right? So some textbooks will say the resting membrane potential is negative 70 millivolts, others will say minus 65, others will say minus 60, blah, 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 blah. Different classes of neurons, different thousand different classes of neurons. Different classes of neurons will have characteristically different resting membrane potentials. Minus 65 millivolts is just a convenient value to use. It's a fairly good average representation across all types of neurons. So what happens here at the beginning is that the microelectrode is outside of the neuron. So the potential, you're not measuring membrane potential, the potential is 0. And then at this point, the electrode penetrates the membrane. And what happens is a virtual instantaneous drop in membrane potential to the resting value of minus 65 millivolts. And importantly, it tends to stay constant. This is a regulated value. The resting membrane potential isn't just randomly fluctuating up and down, it's a regulated value. Okay. Then the question is, what happens if you change the intracellular concentration of the ion? Well, of course, anytime you change the intracellular concentration of a charged particle, that is going to change the voltage. So in this first example, what happens if in this neuron at rest, at minus 65 millivolts, you inject positively charged ions? And it doesn't matter whether the ions are flowing in via physiological means, we'll do that later, or you're just penetrating another microelectrode and experimentally injecting positively charged ions. What happens when you're injecting positively charged ions is that the membrane potential will become more positive, not polarized, it becomes less polarized. Okay? So at this point here, what we're doing for this example is looking at how the membrane potential changes if between here and here, positively charged ions are injected at a relatively constant rate. What happens is that as there's an influx of positively charged ions, the membrane potential becomes more positive. That's not complicated, right? Okay? And the term for that is depolarization. And the idea behind depolarization is anytime the membrane potential is away from 0, away from the value of 0, is polarized. So depolarization is moving it towards 0. One of the nasty tricks in neuroscience is that it's depolarization even if it's going way up here. So anytime it's becoming more positive, anytime the membrane potential is becoming more positive in neuroscience terms, it's called a depolarization, even if that's exceeding 0. Or technically it would be, never mind. You get the idea, right? Definition of term, depolarization. In contrast, questions?
So what about repolarization?
Yeah.
What about repolarization? So like, how does that
Okay. So what about repolarization was the question. So from here to here, basically is the time during which positive ions are being injected at a relatively constant rate. So it takes a little bit of time for reasons I'm not going to explain in this course. The short answer is capacitance, but that's beyond the sketch. Go for the course. Okay. So it takes a little bit of time for the membrane potential to reach a new value. And then when you stop about here, injecting the positive charged ions, then the membrane potential repolarizes back to the resting value. The Y part will be explained later. But, so what happens if, in contrast, instead of injecting positively charged ions, you're injecting anions, negatively charged ions? Well, they can then the neuron more electrically negative, and so what happens is that the membrane potential becomes more negative here. Okay. Stays negative during the time that negatively charged ions are being injected. Okay. The term here is hyperpolarization, moving the membrane potential further away from zero. That's a hyperpolarization. These terms will get used a lot. Depolarization, hyperpolarization, sometimes several times in the same sentence. You need to get to the point where you understand what depolarization and hyperpolarization mean. All of this is intuitive. Okay. So that's a hyperpolarization. At this point, stop injecting the negatively charged ion and the potential will go back to the value. So that's two of the 4 ways that you can change the membrane potential. The others are summarized right here. Okay? So, depolarization means the membrane potential becomes more positive. Hyperpolarization means the membrane potential becomes more negative. As I already explained, if there is a positive ion influx, whether it's a physiological influx through ion channels or whether it's something induced, then what happens is the membrane potential becomes depolarized. On the other hand, positive ions can also leave efflux. And if there's a loss of positively charged ions from inside to outside, the result of that is that the membrane potential becomes more negative. Right? Positive ions come in, depolarization, positive ions go out, hyperpolarization. Negative ion influx, that's the example I gave you before, previous diagram, now here. If there's a negative ion influx, that results in hyperpolarization. Negative ions flowing in, the membrane potential becomes negative. But in contrast, if there's a loss, if there's an influx of negative ions, and if negative ions leave from inside to outside, that can cause a depolarization of the membrane potential. Okay. So, two ions, two forms of ions, positive, negative, they can flow in, they can flow out. You need to know which way the membrane potential changes. Okay, so what maintains the charge separation? Well, that's the little membrane. You might think that's just because it's a physical barrier. It's more complicated than that because there are substances that can flow rather freely through the cell membrane. Ions cannot. Okay? And that is because of the physical structure of the cell membrane. Okay? And so here's the neuron. Here you have an insert showing the lipid bilayer. This is extracellular. This is intracellular. This is even larger expansion where this would be extracellular. This would be intracellular. And you have the phospholipid molecules that the cell membrane is composed of. And so what's important is that the phospholipid molecules are polar in and of themselves. They have a polarized positive phosphate head region and electrically neutral lipid internal region. So this part, the extracellular part, as well as the intracellular facing part of the phospholipid molecule is polarized, the charge on it. In contrast, the intracellular part, the lipid part, is electrically neutral. And as a result of that, the phosphate heads of the molecule are hydrophilic, water-loving. The lipid part of it is hydrophobic, water-fearing, if you will. And as a result of that, if you take disaggregated phospholipid molecules, merely dump them into an aqueous solution, they will spontaneously form into a lipid bilayer, where the electrically neutral parts of the molecule are excluding water, that hydrophobic portion, right, excluding water, and the hydrophilic phosphate heads are in contact with water. Indeed, under most circumstances, if all you do is dump these molecules, these disaggregated molecules, into water, they will spontaneously form a sphere. So what the heck does that have to do with the fact that the anions will pass through? Well, the ions, not the anions and cations. And the reason for that is because the anions and cations, the ions are by definition charged, and therefore they are hydrated. They are surrounded by water molecules. And so the water molecules that are surrounding the ions cannot pass through the hydrophobic lipid interior portion of the cell membrane. So that's the actual barrier. The barrier to the passage of ions through the cell membrane is the hydrophobic lipid interior portion. That's all very well and good, but neuroscience isn't very advanced if that's all that existed. There need to be mechanisms for anions to pass through the membrane, and those are the ion channels. There. Okay. And I'm just using one ion channel to represent all types. Okay. So here you have the lipid bilayer, okay, and this represents an ion channel. The defining feature of the ion channel is that there's a pore in the center, and when that pore, when that channel is open, ions will flow through. So in this particular diagram, this represents the pore through the channel. Okay? And so these ion channels can exist in open states or closed states. So you can think of them like a donut. And so if I'm using my hand to represent an ion channel, this would be the open channel. The channel can be closed. The channel can be open. When the channel is open, ions can pass down their electrochemical gradient. Electrochemical gradient and electrochemical gradient. Okay. So, ion channels. By definition, the pore, through which, when they're open, when the pore is open, ions will flow through their electrochemical gradient. These ion channels can be open or closed. And in addition to that, the ion channels are selective for which type of ion can flow through the channel when it's open. Some of these ion channels will allow sodium to pass through. Those are called sodium ion channels. Others will allow chloride to pass through. Those are called chloride ion channels. Some will allow potassium to pass through. Potassium channels, blah, 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 blah. And also there are some of these channels that will allow multiple ions to pass through. So some of the channels will allow both sodium and potassium to pass through, et cetera, et cetera, et cetera. There are scores and scores of different types of channels that have different kinds of characteristics of what kind of ions pass through with open pores. And just so you get an idea, the evidence suggests that when these channels are open, that the ions will pass through one by one. So these channels are very, very narrow, just open enough so that the ions can pass through one by one in single file. In many cases, actually so small that the height that the water molecules will strip off as they pass through. Okay? So there are two other general categories of these ion channels. I already mentioned earlier. There are the ligand-gated ion channels, and there are the voltage-gated channels. So the ligand-gated ion channels are those that are opened by a molecule or sometimes two molecules of neurotransmitter. So here, for example, this is the intracellular side of the inside of the neuron. This is outside of the neuron. And so if this is a receptor, if this is, in this particular example, a ligand-gated ion channel, then a molecule of neurotransmitter could bind to a specific binding site on the extracellular base of the channel, and when the transmitter binds to that specific binding site, the channel will pop open. When the molecule or transmitter separates from the binding site, the channel will close. That's one class of ion channels. That is the transmitter-gated, or also more broadly called the ligand-gated ion channels. The other kind of ion channel, the other kind of major class of ion channels, are the voltage-gated ion channels. They're not opened by neurotransmitters. They're opened by changes in membrane potential. Most of the time by a depolarization across the membrane. So if this example was a voltage-gated transmitter, a voltage-gated ion channel, then at rest, at minus 65 millivolts, typically the voltage-gated ion channel would be closed. But as the membrane potential became depolarized, say from minus 65 millivolts to a more depolarized value, say minus 55 or minus 40 millivolts, then that depolarization would cause the voltage-gated ion channels to pop open. Those are the kind of channels that cause action potential. The voltage-gated ion channels are the ones that cause the action potential. The transmitter-gated ion channels are the ones that synaptic potential. Back to that table I showed you at the beginning. Okay. Wait a minute. I think we're supposed to be resting membrane potential. Did I forget? No, it took a while to get there. There is this third type of channel. Okay. Not previously mentioned, and that is a leak channel, more specifically a potassium leak channel. And the characteristic of the potassium leak channel is that it's permeable, most permeable to potassium, and it's called a potassium leak channel. And the other characteristic is that its default state is open. So the other kind of channels, transmitter-gated and voltage-gated channels, the default state of those channels is closed. It takes something, a depolarization, or a transmitter to cause them to open. The potassium leak channel default state is open. These channels exist throughout the neuronal membrane. So the potassium leak channels exist in the membrane of the dendrites, in the membrane of the soma, in the membrane of the axon hillock, in the membrane of the axon, and the membrane of the membrane of the presynaptic terminal. Basically, they're everywhere. And as a result of the existence of these potassium leak channels, At rest, at minus 65 millivolts, the membrane is most permeable to one particular ion. The particular ion that the neuron is most permeable to at rest is potassium. And so potassium is critically important. The high permeability of the neural membrane to potassium is critical for setting the value of the resting membrane potential. The reasons that I will about to explain. About to explain. Right? So, topic. We're now talking about potassium, talking about resting membrane potential, and the question is, why is it that the high permeability of the membrane potassium is so important in setting the resting membrane potential of minus 65 millivolts? And it goes through a bunch of steps. Bear with me. Okay? It's simple. So here we have the neuron, okay, representing this blue cylinder here. And the physiological concentration of potassium, this is mammalian, some textbooks will give different concentrations of the ions, particularly with invertebrates, so invertebrates will use concentration. Okay. The concentration of potassium is much higher inside the neuron than outside the neuron. Typical values of potassium intracellularly are 100 millimoles versus 5 millimoles outside, right? So 1:20 ratio being the concentration difference. And so under this condition, the diffusional force, and the diffusional force here is represented by an arrow. Okay? The diffusional force considered alone would cause potassium to leave the neuron. So there would be, under these conditions, an efflux of potassium. That efflux, that loss of positively charged ion, would cause the membrane potential to become more negative. Right? Straightforward. Diffusional force, rounding motion, substances typically slow down their concentration rate. You know that since middle school or high school. But it's not really that simple. So here are 4 examples that are basically setting the stage, help you understand the forces that underlie resting membrane potential. Also is actually the same forces with different ions that underlie synaptic potential and action potential. Okay? So what I'm doing here is I've got neuron cylinders, representing neurons at 4 different membrane potentials. 0 millivolts, like the starting voltage. 0 millivolts, minus 40 millivolts, minus 80 millivolts. That's kind of close to the resting membrane potential, not exactly, but close. And an even more negative value of 120 millivolts. And the question is, at those different voltages, what happens to the flux of potassium through the potassium leak channel? And that's what's shown in red. Okay? If you go to the other side, at this value, at minus 0 millivolts, there's an efflux of potassium, so potassium flux through the leak channel. And a result of that, efflux of potassium, as I showed you before in an earlier example, would cause the membrane potential to hyperpolarize. Same thing would also be true if the membrane potential was minus 40. There'd be an efflux of potassium, again causing the membrane potential to hyperpolarize even further at minus 80 millivolts. In contrast, for reasons I'll get to, there would be no efflux of potassium. And then at a value of minus 120 millivolts, that is anything more negative than minus 80, at a value of minus 120 millivolts, that would actually set up forces that would cause an influx of potassium. And that influx of potassium would cause the membrane potential to depolarize. So general point, potassium can flow out, potassium can flow in, and that depends on the membrane voltage of the neuron. Let's start at 0 and break that down. What causes those different fluxes of potassium that will then change the membrane potential? Okay, this is about resting membrane potential. It also is more expansive than that. Okay, so at 0 millivolts, the diffusional force, right, that is the force of concentration gradient, potassium is more concentrated inside the neuron than outside. And so the diffusional force on potassium will be outside. That's the arrow. Okay? Electrostatic force, first time we talked about that, electrostatic force is a direct function of the membrane voltage. So at 0 millivolts, the electrostatic force is 0. At minus 40 millivolts, the electrostatic force on a positively charged ion is inward. At minus 80 millivolts, the electrostatic force is even greater on a positively charged ion. Positively charged, negatives attract positives, right? And at minus 120 millivolts, the electrostatic force is even greater than before. Okay. Back to the first example, diffusional force on potassium, high concentration inside, diffusional force is outward. At 0 millivolts, there is no electrostatic force, so diffusional force is the only game in town. Driving force is the sum of these two. Right? Driving force on potassium is the sum of the diffusional force and the electrostatic force. So in this case, the driving force equals the diffusional force, so potassium flows out. All very straightforward. And so the result of potassium flowing out, back to the examples I showed you, is that the membrane potential, starting at 0 millivolts, because of the loss of this positively charged ion, will become more negative. So that leads to the next example, the one below. We'll go look at a more negative value. Minus 40 millivolts. I just chose that value, not completely randomly, but you would have no reason to know why I did, right? Take it on faith. Okay. Minus 40 millivolts. The diffusional force is essentially unchanged. One of the important things in the point of confusion for students is that the amount of potassium that would need to leave the neuron to change the membrane potential from 0 to minus 40 is so small that it's not going to appreciably change the concentration rate. The concentration, the cellular concentration of potassium is still going to be very, very close to 100 millimoles. It'd be like 99.999999. Okay, trivial loss of potassium. So the diffusional force is effectively unchanged, driving potassium outward. But here you have an electrostatic force, negative charge, negative voltage, it's attracting the positively charged ion inward, partly offsetting the diffusional force. You have two different forces acting against each other, and so the driving force on potassium is less than it was at 0 millivolts. Nevertheless, the fusional force at minus 40 millivolts is greater than an electrostatic force pulling the positive charged ion in, and so the net driving force is still outward. Potassium will still pull out and further hyperpolarize the membrane potential down to minus 80 millivolts. That's not a randomly chosen number. What it means is when I chose it will become clear later. Okay? At minus 80 millivolts, the diffusional force outward is exactly equal but opposite to the electrostatic force. The electrostatic force is a direct function of the membrane potential. Okay? So the sum of the diffusional force and the electrostatic force is 0, and so at that point, even though you have these open leak channels, there's going to be no net flux of potassium. So if everything else is constant, membrane potential will stay at minus 80 millivolts. So there's no flux of potassium, no effect on membrane potential. And last example here. But what if the membrane potential is more negative than minus 80 millivolts? At any membrane potential more negative than minus 80 millivolts, the electrostatic force that's attracting the positively charged ion is going to be greater than the diffusional force repelling the ion. And so at a membrane potential more negative than minus 80, you're actually going to have a driving force inward that will attract the positively charged ion. So there will be a net influx of potassium from outside of the neuron to inside of the neuron. And the consequence of that, in terms of membrane potential, is that will actually depolarize the membrane potential. So the functional impact of this, the functional consequence of all of this, is that whenever the membrane potential deviates from minus 80 millivolts, that will set up a flux of potassium that will tend to drive the membrane potential back towards minus 80 millivolts. Okay? So in these examples, when the membrane potential was more positive than minus 80 millivolts, that set up a efflux of potassium that tended to hyperpolarize the membrane potential towards minus 80 millivolts. The membrane potential is more negative than minus 80 millivolts. That set up forces that tended to cause an influx of potassium that would depolarize the membrane potential towards minus 80 millivolts. And 80 millivolts is, as we explained in a bit, the equilibrium potential for potassium at the physiological concentration. Okay. Question? So the question is, what's the difference between the resting membrane potential of minus 65 millivolts and the equilibrium potential of minus 80 millivolts? And in no world that I know of does minus 80 millivolts equals minus 65 millivolts. And so the quick ahead of the game explanation is because there is some permeability to other ions, particularly sodium. And so there is a slight influx of sodium that will drive the membrane potential a little bit away from minus 80 millivolts towards minus 65. It'll take a while to get there. Okay. Question? Yes. So the question is, does the driving force directly influence ion. The answer is yes, provided that there's a pathway for the ion to flow. And so because there's the potassium leak channel, then there's a pathway for potassium to flow in or out of the membrane, in or out of the neuron. And so for that reason, the driving force will cause potassium to flow in or out depending on what the membrane potential is. But it takes two things, right? So you have to have a driving force, you also have to have a pathway. And so now that gets into the channels that are open and closed, right? And so sometimes you can have a very strong driving force on an ion, but the channels that will allow that ion to flow through get closed, and so then the fusional force and the driving force are going to be different. But basically, yes, if there's a pathway for the ion to flow, like the leak channel, then the driving force is what determines the rate at which the ions will flow, and we just happen to have the leak channel. It is that permeability, that high permeability of the that high permeability of the membrane to potassium at rest. That is the cause, is the reason that the equilibrium potential for potassium is the major determinant of the resting membrane potential. Question? Would I clarify what? Would I clarify electrostatic forces? Happy to. So, actually, I very cleverly have this here. I can't point to. So, I have learned over the years that students get really stressed out without definitions. So, most of the time I hate definitions because the way science is usually described in terms of definitions is the worst possible way of doing it. Anyway, so the question was the driving forces, electrostatic forces. Thank you. Great memory. Cell, right? So the electrostatic force here is a direct function of two things. One is the membrane potential. Okay, so minus 40, minus 80, minus 120. The electrostatic force is a direct function of the membrane potential and the charge on the ion. So in this case, we're talking about potassium, a positively charged ion. And so, the opposites attract. Okay, so a negative intracellular membrane potential will attract a positively charged ion. But if instead we were talking about chloride, a negatively charged ion, an anion, then a negative membrane potential would actually produce a repulsive force on a negative ion. Okay. For directly for definitions, the electrostatic force on an ion is produced by the membrane voltage. The amount and direction of force is a function of the membrane voltage and the charge on the ion. Okay? And going to the other definitions, the fusional force is the force on an ion due to its concentration gradient is the ratio of extracellular to intracellular concentration of the ion. And the general point here in neuroscience is that the diffusional force rarely changes significantly under physiological conditions. Right? So the fluxes of ions that can dramatically change the membrane potential. Millivolts can dramatically change the membrane potential. Don't appreciably change the diffusional force. Don't appreciably change the concentration gradient. We'll change it to some trivial amount. It's very, very small. You can effectively think of concentration gradients for most of And the driving force on an ion is the sum of the diffusional and the electrostatic force. There is a simple math for calculating the driving force. It's not just some construct, right? It's calculated by the formula. The membrane potential minus the equilibrium potential of the ion. Membrane potential minus the ion equilibrium potential is the force that controls the rate of ion flux if, notice the if is capitalized, if the membrane is permeable to the ion flux and also the membrane potential. And then ion flux, the mechanism by which the membrane potential is changed, is controlled by the driving force. Driving force and the permeability of the membrane to that ion. These are all in the notes, by the way, so don't worry about writing them down. I like to do that. I always find it useful for learning. Okay. And then the big bottom line is the importance of this functionally about equilibrium potential. So a lot of this is nuts and bolts, right? Nuts and bolts, how to figure it out, what are the parts. So what is it that you need to understand about equilibrium potential? How do you help you on the exam, for example? And more importantly, from my side of things, understand how neurons are working, how synaptic potentials work, how action potentials work, is the bottom line down here, the equilibrium potential. And the importance of that is that the membrane potential is always driven toward the equilibrium potential of the ion to which the membrane is most permeable. So here we're talking about resting membrane potential. The membrane is most permeable to potassium. So the membrane potential is driven towards the equilibrium potential of potassium because the membrane is most permeable at rest to potassium. However, during action potential, the membrane becomes more permeable to sodium, and so then the membrane potential will be driven towards the equilibrium potential for sodium, and then it becomes more permeable to potassium, more so than through the leak channel. Then the membrane potential will be driven towards the equilibrium for potential potassium, and so on and so on and so forth. So the permeability of the membrane changes rapidly. But what's the difference between the driving force and what? What causes the channel to become what? Open. What causes? Sorry, I have to deal with 63-year-old ears that are ringing all the time. What causes the channel to be open depends on the kind of channel. If it's a voltage-gated channel, then depolarization will cause the channel to open. If it's a ligand-gated or simply a transmitter-gated channel, it's the binding of the transmitter. Now, I said that the potassium leak channels, the default state is open. They can be open and closed like intracellular signals, but that's really beyond the scope of the course. Okay? And sometimes adding too much just makes everything fall apart. If it was a chloride, it would depend on the concentration gradient and the charge of the ion. Fluoride is actually more concentrated extracellularly than intracellularly, so most of your would be. We'll go through examples of that. So I think you're going to get sick of seeing these examples. I'm going to go through them with synaptic potential, then I'm going to go through them with action potential. Right? well. I must have gone through that at blazing speed because I guess we didn't talk about Nernst equation. So this gets directly to a question that was asked there. And right here, so question that was asked over here, minus 80, minus 65, same resting membrane potential given negative 65 millivolts, I equals minus 80 millivolts. So we're explaining the difference. And so that's exactly the question that's posed right here. And the answer to that is that there are other ions involved that do have some permeability. And this right here tells you what these ionic concentrations are. And as much as I hate memorization, these are values that you should memorize. Okay. So here, this is representing a neuron, cell representing a neuron. So these would be the intracellular values. Up here would be the extracellular values. Potassium, sodium, chloride, calcium. Then down here you have the ratios, which actually turn out to be more important than the absolute concentrations. Here are the equilibrium potentials for the ions, and here's the permeability of the membrane to these different ions after that. And remember, the permeability change rapidly. Okay? So start with the one we already went through. For potassium, as I already mentioned, the intracellular concentration is roughly 100 millimoles versus 5 millimoles extracellularly. So the ratio of potassium outside the end is 1 to 20. And as a result of that, for reasons that you'll see in a bit, the equilibrium potential for this particular ion, the equilibrium potential for potassium at these concentrations is minus 80 millivolts. Okay? And when the neuronal membrane is at rest, because of the lead channels, the neurons are most permeable to this particular ion. Okay? For sodium, in contrast, the extracellular concentration is much higher than the intracellular concentration. 150 millimoles out versus 15 in, that's a concentration rate of 10 to 1 out to in. And as a result of that, at these concentrations, the equilibrium potential for sodium is plus 62 millivolts. So here, potassium, you have negative value. For sodium, you have positive value. However, at rest, the permeability of the neuronal membrane to sodium is about 1/40th of the permeability permeable at rest. At rest, for other times when that changes, at rest, the local membrane is much more permeable to potassium than the other ions. Okay. And then the chloride, sodium chloride, the cellular concentration is similar, sodium 150 millimoles out versus 13 intracellularly, ratio of 11.5 to 1 out to in. The equilibrium potential for chloride at these concentrations, I keep saying these concentrations, because the equilibrium potential is a function of the concentration of the ion. So the concentration of the equilibrium potential for chloride at these concentrations is minus 65 millivolts, which just happens to be the resting membrane potential, even though chloride plays very little role in setting the resting membrane potential. And the permeability of chloride at rest is 1/10 of the permeability of the membrane to potassium. And then for calcium, note here you have a divalent cation, so unlike sodium and unlike potassium, you have a monovalent cation. Here you have a divalent cation, which becomes important in the Nernst equation. Okay. The concentration here, the cellular concentration of this ion is very low, 2 millimoles. The intracellular concentration is extremely low. Okay. 10,000 millimoles. And that means that the ratio of this ion, the extracellular and intracellular, is higher than any of the others, 10,000 to 1. And the equilibrium potential for this ion is positive 123 millivolts. Permeability at rest is essentially zero. Okay. So the answer to the earlier question about why the resting membrane potential is at minus 80, equilibrium potential for potassium, is because there is a slight permeability of the membrane at rest to sodium. There. And so the resting membrane potential is driven slightly more positive than minus 80 towards minus 65 millivolts. Because that slight permeability of the membrane to sodium will drive the membrane potential in a more positive direction. Okay. So that's the short answer on resting membrane potential. Finally. So let me give you a quick introduction to the Nernst equation, and cut it in half, and pick it up next time after you've had a chance to reading from the Nernst equation. Okay, and read about all the stuff I talked about today, which is mostly chapter 3 of Okay, so the Nernst equation is an equation that's used to calculate an ion equilibrium potential. And one of the things in the course that I try and do is I try to minimize the math as much as possible. But for those of you that are neuroscience majors and are going to go on to take like cell biology neuroscience 120, the Nernst equation is foundational for a bunch of other mathematical things that we need to do. So just to provide a foundation, I'm including that in the course. Okay. You need to know calculations in a simplified version of the Nernst equation that I'll give you later. Okay. But for the midterm and the final, you can use calculators, but the problems are set up in a way so that you should be able to solve them intuitively without actually using a So this is the formula for the Nernst equation. The equilibrium potential of an ion is a correction value, 2.303, over RT over Ts, and the log of an extracellular concentration of an ion over the intracellular concentration, where E of ion equals the equilibrium potential, R here equals the gas constant, T equals the absolute temperature here, F equals Faraday's constant here, and Z equals the charge of the ion. I will tell you in advance that you do not need to know the gas constant, you do not need to know Faraday's constant, and you do not need to know the absolute temperature. You will need to know the charge of the ions, and you will need to know the concentration of the ions inside and outside of a simplified version of the Nernst equation. So you get a constant temperature, all these things null out. Okay. So intuitively, and go back to this over and over again, because one of the most important ideas, important concepts in the course, is that intuitively the equilibrium potential of the ion, the voltage and the electrostatic force, will counteract the ion's diffusional force, right? So it's where the diffusional force and the electrostatic force are equal but opposite. That's the intuitive answer. Equilibrium potential. So they're equal but opposite. Okay. And then increasing the concentration gradient or temperature will increase the equilibrium potential, right? So these are constant. So as the temperature changes or the concentration gradient changes, right? Concentration gradient changes or the temperature changes, that will change the equilibrium potential. And similarly, ions with twice the charge will have half the equilibrium potential, right? The value of the charge of the ion. So think about that divalent cation, calcium, versus monovalent cation. So I think that's enough for today. I accidentally let you out 10 minutes early last time. We were realizing what the time was.